Okay, we can get started. Start recording. Okay. Okay, so you can hear me, right?
Yes, sir.
Yeah, okay. So let me summarize. It's been quite a few days since we had our last class. What we have done, what we have covered so far, on this topic of temporal logics. We started with transition systems, or more specifically, Kripke structures. Okay, introduce that to define the behaviors of interest for our transition systems, okay, or models. So we define specifically two kinds of behaviors: linear behavior, which were characterized, defined as traces generated by the transition system. So these were defined as a set of all infinite label sequences induced by legal executions starting from any of the initial states in the transition system. Then we defined what a branching behavior was, and this was defined as a set of computational traces or computational trees, if you wish, which is defined as a set of all infinite label computation trees induced by branching executions of a transition system. So, and the purpose of introducing temporal logic was as to be able to specify some constraints on our behaviors to denote our expected behavior. Okay, so these are what we call as specifications or constraints on behaviors. We call them as properties as well. So there, once again, depending upon whether we care about constraints on linear traces, linear behaviors, or branching behaviors, we introduced, the two class properties: linear property, which are defined as a set of infinite label sequences. Okay, that makes a set of all infinite label sequences that make that formula true. Okay, and sometimes this set is denoted as the words characterized by the formula phi. Okay. And a branching property is defined as a set of infinite computational trees generated from a root, each of which, the collection of which makes, I should be saying each of which, the collection of all the computation trees are the ones that make phi to be true. And this is usually it is associated with states in the Kripke structure, and therefore it is defined as the set of states that satisfy the branching property. Okay, that's how we define. And then we introduced CTL star, and this is a propositional temporal logic. Okay. By the way, why do we call it propositional? Why do I call it propositional? Anyone could? Yes, why do I call it propositional?
The domain is true and false.
Just one moment. Ganesh, சொல்லுங்க. பார்க்கலாம். Okay. Thank you. Yeah. What was the answer?
The domain will be true and false, right? Similar to QBF.
Yeah, not exactly. See, you remember that how these things are constructed. What are the atomic propositions? The atomic formula here are propositions, correct? There are only finitely many propositions. Just like propositional logic, it is built using the usual logical connectives, and the atomic formulas are all propositions. Here also, the atomic formulas are all just propositions, so only finitely many, okay? Yeah, in that sense, yes, the atomic formulas are sorry. Yes, and that's the reason. See, if your atomic formulas allowed quantifiers or something like that, okay, then it is no longer. But what is in addition to the usual logical connectors, we allow temporal operators, okay, as well as quantification over paths, okay, that is built. But at the atomic level, they're all propositions, only finitely many. So as a consequence of it, at the atomic level, you're only able to distinguish or characterize only a finite number of states, okay? And it's precisely called propositional temporal logic because the whole thing is built on top of, at the atomic level, using only a finite set of propositions, okay? So that's how it is. It's built. You can have quantifiers. You can have temporal operators. That whose interpretation is over paths, and then you can quantify over paths. Okay, originating from certain states. Yeah. Then we introduced two sublogics of CTL star. So CTL star is a propositional temporal logic that can specify both kinds of behaviors, okay, or a combination, constraints over both kinds of behaviors. And we introduced two sublogics. One, LTL, specifically LTL, which is a sublogic that can specify constraints on linear behaviors, which means that an LTL formula really denotes a set of infinite linear traces. And CTL is a sublogic that can specify constraints over branching behaviors, and their interpretation is given as the set of states for which the behaviors originating from that state satisfy the constraint defined by the formula. Okay? Any questions here? Okay. Summarizing. Yeah. So usually I also kind of define two notations. Okay. In one of my earlier slides, I use this double square bracket around either a model that is a Kripke structure or a formula, okay, to denote actually the behavior generated by that. So when I use double square brackets with a model, a Kripke model, in that what it means is it's actually the traces, linear traces generated from by the model, which means that linear traces generated from any one of the initial states as defined. So just to align with the two kinds of notation, that's all. Set of all infinite label sequences induced by all the legal execution starting from any one of the initial states. The branching behavior, if you're concerned with branching behavior, they are computational trees, usually generated from any of the states. And that is usually defined as a set of all infinite label starting from the set of initial states. A specification is constraints on behaviors. So linear property means it denotes the set of labeled infinite label sequences, okay, that make the formula phi to be to be true. Similarly, branching property is usually defined as the set of states, okay, that such that the computational trees generated from those states correspond to those that make phi to be true. So the model checking problem, usually we denoted it twice. Given a model, it is the problem of checking if that model satisfies a given formula in that logic. Okay, so which really means if you so phi defines a set of defines a behavior. So that, how we have defined that using the formal semantics of the logic. And then you take the executions and then you consider the set of traces that are induced by the model. Then, this is equivalent to checking if that the set of traces defined by induced by the model is actually contained in the set of traces defined by the formal semantics given to that logic. And that's how it is formally defined. So you can consider this is when you want to define it as a satisfaction problem, this is the same thing. You collect all the behaviors that satisfy either the traces or infinite trees that satisfy that make phi to be true, and then you check if the set of traces generated by the model is contained in that. Okay, so for the CTL star and CTL, this problem is becomes one of checking satisfaction in that model from any one of the initial states. So if you now gather all the states that satisfy the formula, the CTL or CTL star formula phi, there is one of checking that your initial state should be contained in that. An LTL model checking problem, another way to view in terms of traces is you now, you get the words that are, the set of words that make phi to be true, and then you generate the traces from the model, and then you check this subset. Okay, so that is So the model checking. We have really not talked about model checking problem. We are still trying to acquaint ourselves with formulas in these logic, specifically about specifications and properties. Any questions on the way that I have summarized the model checking problem? Okay. So even before we talk about the actual model checking, how you do model checking, I mean, this problem of question of given two formulas, if they are equivalent or not, is relevant. And there are two ways of defining. We say that phi1 and two formulas, phi1 and phi2, in any of these logics that are equivalent. Notice that. So the LTL, if you want to convert it into a kind of express it in terms of CTL star or CTL, so what you have is you just make a, get a CTL star formula, okay, by putting a universal path quantifier around it, and then, then you check the corresponding CTL star formula, which effectively means since we have defined traces of M to be all those traces that are linear traces originating from the initial states, this becomes one of checking if whatever the constraints that it imposes on these infinite traces is that those traces that are contained. Okay, so then the question of equivalent becomes either you could say that okay, the behavior that are denoted by phi1 and phi2, the interpretations, they are equivalent. Or another way, to say is if phi1 and phi2 are said to be equivalent, if they are equisatisfiable for all models M. That is, for every model M, either both formulas are satisfied by the model, or they are unsatisfiable by both those formulas. That's what that's another way of viewing it. Therefore, when we
is the meaning of equisatisfiable here different from the one used typically in logic? Because in our logic course, we understood we learned that two formulas are equisatisfiable if the existence of a model for one implies that another model, which may not necessarily be same, exists for the other.
no,
because we learned the formula P and the formula not P, both of them are equisatisfiable, because if you find a model for one,
no.
that's it.
The equisatisfiability, the way I'm defining is two formulas are equisatisfiable if when one is satisfiable, if one is satisfiable by a model, the same model satisfies the other one. Okay.
So it's the same thing as equivalence.
Yeah.
Okay. In our logic course, it was different, so I was confused.
No, why is it? In classical logic, the equivalence means if you make one formula, if phi1 is equal to phi2, if phi1 is false, the other one should be false too. If phi1 is true, the other one is true. So what does it mean to say phi1 is true? That means that there is no, I'm not saying that phi1 is, if phi1 is satisfiable, then phi2 is satisfiable, okay? And if phi1 is not satisfiable, then phi2 is satisfiable on every model, okay? So what does it mean to say phi1 is true on a particular model? Huh? So how is it? How was equivalence? They should be true for every model. Either that one should be, if it is true, the other one should be true as well. If it is false, then the other one should be false. That's how equivalence is defined, isn't it?
Yes, but equisatisfiability is not.
Okay. So you're saying equisatisfiable if whenever one is satisfiable, the other one should be satisfiable. Okay?
Yes, but they may not necessarily agree on every single model. It's just that.
No, they don't have to agree on every single model. That's why the way I define equisatisfiability is whenever one is satisfiable, the other is satisfiable. If one is unsatisfiable, the other should be unsatisfiable too.
Yeah, but the definition in the slide seemed, I think that is equivalence. Because
we are saying equisatisfiable for all models, does it make a difference?
No.
If it's equisatisfiable.
No. See, equisatisfiability is about a pair of formulas, okay? So when you say a formula is satisfiable in all models, that is validity, okay? So if it is equivalent, this is equivalent, okay? So whenever, yes, okay? So for every model, so equisatisfiability is okay. So whenever there is a, so I guess the distinction that you're making is, so if it is unsatisfiable, so there could be two different models. If it is,
the model that satisfies phi1 might be different from the model that satisfies phi2.
Phi2, no,
If
okay. That's not how. So maybe that I have to be careful. Okay. So yeah, if you allow for that, that is not. So the way I'm defining it is exactly equivalent. Okay, correct. Yeah. Okay. Because I'm doing it for every model. So every model, if the formula 1 is satisfiable in that model, for that model, the other one should be satisfiable as well. Yeah.
Okay.
Yeah. So in that sense, this is the equivalence. Yeah. Okay. So forget about EQ satisfiability. So if we allow for EQ satisfiability as, see, if the two have the same formulas, okay, I mean the same set of variables. So let's look at prepositional logic. Okay. Yeah, the way equisatisfiability is, I haven't checked this. Okay, so equisatisfiable is if one is satisfiable, if they have the same set of variables. So what you're saying is equisatisfiability is just whether one is satisfiable or the other one is satisfiable. Okay. So there could be two different models that can make it satisfiable. No, that's not how I'm defining equisatisfiable. Okay, so so I'm defining it as equivalent. Let's not confuse. Okay, yeah. So this corresponds to equivalence. You're right. Yeah, if you define equisatisfiability, you allow that two formulas are equisatisfiable if you allow for one to be satisfied with one model, the other one is, see that, are you sure that is how equisatisfiability is defined? Because equisatisfiability means whenever one is satisfiable, the other one, if you define it as the other one is satisfiable, but on a different model, then that's not what I mean here, okay? So let's keep it as equivalence, okay, for now here. So, yeah. So yes, okay, good. So which means proving, so we agree on that?
Sorry, could you repeat?
No. Let's remove the equisatisfiability since there is two different interpretations. This is what I mean, okay, when they are equivalent. Yeah.
Okay.
Yeah. So what I mean is that for every model, if one is satisfiable, for the same model, the other one should be satisfiable as well. If so, one way, so there are three ways of showing. This is what I mean here is by equivalence. Okay. So show equivalence on set of behaviors, you can just look at the set of behaviors and then say they're equivalent. Or you can use laws of equivalence to transform one to the other. Or show no two models can distinguish them. Okay. That is, on every model, if one is satisfied with the model, so is the other formula. Or on the same model, if one is satisfied, the other one is not satisfied, then we say that it is then they are not equivalent. Okay. So you could say that they are not equivalent if you could show the existence of a transition system for which one is true as per this satisfaction, and for the other that it is false. Yeah. So these are three ways of showing. Agree? As per this definition, remove the equisatisfiability since we have a difference in what we interpret. Okay, just assume that we have equivalence defined as follows. Okay, as given by this. So given that, then these are three different ways to show. Agree?
Yes.
So given this notion of equivalence, this is the relative expressive power of these languages. Okay. So CTL star is the largest class of things. So both CTL and LTL are sub-logics, strict sub-logic of CTL star. And you see CTL and LTL are incomparable because, I mean, each of them has some formulas which is not representable or expressible in the other logic and vice versa. Okay. And of course, there are some, which there's some intersection of, LTL and CTL here, where they are equivalent as per the previous definition. Okay. And that is, you would think that, CTL, since LTL does not allow path quantifiers, you probably would have thought that CTL might be strictly more powerful. Okay. I mean, the fact that CTL star contains LTL is not surprising because it contains the entire, all the formulas constructed out of strictly the linear time operators. Okay. And CTL is a subset of CTL star because it restricts the way the path quantifiers are applied and juxtaposed with the linear temporal operators. But what is somewhat surprising is that these LTL and CTL are incomparable, and that is something that we will, we will see some examples of in today's class. Okay. Okay, so first, before that, let's, I will just, I mean, I'm calling it a CTL versus LTL. I will get to that, but here it's just all CTL formulas, okay? So, as, class exercise, I just was, thinking I had drawn some pictures and I wanted you to review that, okay? So let me, I've already given those pictures, but I still wanted to ask each of you. So how is one here? Yeah, this is just CTL to CTL comparison. So I'm just, I'm going to ask you, so describe to me how 1 and 2 are different. In what? I mean, on a particular model, they could be equivalent. I mean, on a particular model, equivalent in the sense either they are both satisfiable on that model or not satisfiable. So here, when I say so, so why is AG of AFP different than AG of EF of P? So let me go around, start with Paramala, okay? So if you were to, I'm asking you to explain why is AG of AFP is different than AG of EF of P, in what sense?
I can give an example model that which satisfies the first one, but doesn't satisfies the second.
Yeah, you have to say that, okay, it includes some patterns of infinite trees which one satisfies but the other one does not satisfy. That's how I would describe. Okay.
But you want to tell me the differences by words?
What?
I have an example model that satisfies the second property, but that doesn't satisfy the first property. But I don't know how to solve it.
Oh, it satisfies the first.
No. Satisfies the second, but doesn't satisfy
Yeah.
the first.
Okay. So okay. So yeah, I mean, you could describe that, or can you give an intuitive thing? Intuitive explanation.
So intuitive explanation would be the first one says that every path starting from the initial state and every state in those paths, which means every state in the transition system should satisfy the property A of B. And
Yeah.
so it is quite equivalent to every state in the transition system should satisfy A and B. And the second property states that every state in the transition system should satisfy E F P. So second one means that every state in the transition system should have at least a path starting from it, which eventually will satisfy P. The first one means all the paths originating from every state should eventually satisfy P. And one implies two. If a state satisfies the first one, it will eventually.
You're right that one implies two in the sense that on every path, P should occur infinitely often, correct? So it is not, although, see, this picture that I have here is a bit, confusing, okay? So strictly speaking, so this is, you see, on every path, this cross, the P should happen infinitely often. That's what AG of AF of P means, okay? Because in every state you should eventually, yes, the way you described is correct, okay? So this is how, so it should happen. So I mean, all this particular cross is covered by all these things, yeah? But on that path, the states that occur after that should also have a state that satisfies P. Here, cross are those states that satisfy P, correct? So, so that's why it has these kind of a cascading thing, yeah? It's not, so every state should satisfy, as opposed to, so, that's what, so, so there'll be some cascading thing, whereas here, it is, on every state, it is enough if you have, one thing that satisfies. For example, in 2, there is a path here, okay, the leftmost path in which P never holds good eventually, correct? Maybe is that what you meant, okay? Whereas because as long as there is one path in which eventually, a P, P holds, okay? So, because here eventually P holds here, and therefore, although it never holds on this thing, okay? So every state you will have to have, there exists only a path, okay? So this particular state, for example, need not have, there is one path on the left side in which P never holds, okay, eventually. But that's okay as long as P holds here, okay? So you see the difference?
Yes, sir.
Okay. Okay, so you're right that one implies two. So because this requires that every state has to have eventually something, whereas here it is enough if one one path has that. Okay, so let's move on. So so how is 2 1 different from 3? Okay.
How is 2 different from 3 or 1 different from 3?
Well, choose one. How is well?
I
2,
think it's easier to say with 2 and 3 because
2
only
and
one.
3.
Yeah,
Correct.
EGF
Yeah.
and EGF.
Yes. Yeah. So take, yeah.
Like for 2, it means that it's given AG. So because of that, every path from the start state should satisfy the GEF. But because in 3 it is given as EG, only a single path is required to satisfy GEF. So there could be many paths where like F is eventually F is unsatisfied. Like it's not there.
Yeah, like here, they could be, see, for example, there could be paths where F is never true. Okay, so whereas here, see, so for example, when you compare 1 and 3, 2 and 3, it's easy, as you said. 1 and 3 is also, in some sense, easy, isn't it? Because 1 and 3 is also easy, isn't it? See, because if there's actually one property, see, AF of P always implies EF of P, correct?
Yes.
And AG of any formula G implies EG of any formula as long as G1 implies G2. Okay, so you can actually use that to do that. So this is what I'm stating. Okay. See, for the same formulas, AG of G is always implies EG of G. Okay, for any CTL formula. Okay, so as a matter of fact, if G1 implies G2, then AG of G1 implies EG of G2 as well. And since AF of P implies EF of P, you can also say that 1 implies 3, correct?
Yeah, but 1 already implies 2, right? So 2 implies.
Yeah, 1. Yeah, because AG. AG of G. Because once again, G1 because AF implies EF, no? That's why. Okay. Therefore, AG of that has to imply AG of EF as well. Okay. So AF of P implies EF of P, and I'm claiming that AG of G1 implies AG of G2. If G1 implies G2. If AG both are the same thing, then they'll have to imply that for any state look at, for any state, if yeah, and I think these things occur because you can actually, because of this thing. So 1 implies 2, as well as 2 implies 3. So 1 implies 2 implies 3 is true. Okay, so and that is also the reason. So Ratnakar, so talk about 2 and 4. Okay.
Yeah, so 4 is saying that from the root there is some path such that on every state which you encounter on that path, every state you can reach phi through you can reach phi through some path, like through every single path that starts from that state. 2 is saying I think 2 and 4 are incomparable. I don't think like 2 implies 4 or 4 implies 2.
Correct. That's so. This thing is actually wrong. Okay, but intuitively, EG of AF of P is really something like this. Okay, like this. See, on this, there exists a path from the root in which it is globally true. Okay, every state should be such for that AF of P should be true. Okay, which means that for every state, eventually P should hold good. So all these states here on this path are covered by this. But now, if P becomes false again on that path, then there must be another path on which it becomes it becomes true again, and so on and so forth. Okay, and then that has to do. So intuitively, another thing is there must be at least one path starting from the root on which P occurs infinitely often. Okay. On the other paths, it doesn't matter. Okay. So on the other paths, it is on the other paths, as long as there is one path in which if P is true. So on the other paths, it really doesn't matter. I mean, either you can have EF of P true, or it can even be that P may never be true, no? So suppose there is a path, I mean, as long as there is something like this here, and if there is a path here, say, on the left, here I've at least crossed all the ones. Is that required, Ratnakar? So that's what I'm,
Could you repeat your question once?
No, can I have, suppose I change this behavior to such that there is one path here, like say the leftmost, on which P never occurs. Would that still satisfy EG of EF of P? That's just a side.
As long as you have some path for which phi always occurs, it shouldn't matter. Like
like as long as there is one path here, like I've shown here, on which P occurs infinitely often. Okay, so on this path, it doesn't matter because it is for this state, the second. The successor on the right side here, okay, that I'm pointing the cursor to, for that AF of P does not hold good, correct? Although I've shown it as holding good here, okay, because I've crossed everything, but it doesn't have to, is all I'm saying. I mean, I'm asking you the question, if can I have no cross on a path forever here and still have AG of AF of P true?
Yes, it will still satisfy EGAF.
Yeah, EGAF, correct. And the reason that you said that two, because once again, AG is EF. Okay, so they're incomparable. Why? Because
in the example you just gave, I can use that. If in that example 4 is satisfied, 2 is not satisfied.
in this.
Suppose you have a path like you described in which you never encounter 5.
Yeah.
4 is satisfied, 2 is not satisfied because you have it's not the case that every single path you can reach 5.
Yes, because that has AG, correct?
Yes, AGEF.
Yes. Okay. Yes. Yeah. So because on that, every path, there is, but then, yes, I can make, so in this case, just by making no crosses on the leftmost thing, it is, I still have, since I have crosses on all the other things, there exists a path, okay? For EF, correct?
Yeah, like if you don't put any crosses, then it will work. Like
Yeah.
there is a single path. With
Yeah, you should not put crosses on all these things, except one that I have actually shown here. That is, still satisfies EF, correct? Yeah. So if you just remove it, I guess he's correct. Okay. Yeah. So even if you remove all the things, remove all of them, then it'll correct. If I remove crosses on all of them,
Except the path that you've shown, the middle path.
yeah. So AG of EF will not be satisfied, correct? AG of EF.
I think it is a little harder to reason looking at the computation tree than looking at the states themselves, because we won't be seeing every single path from the computation tree, right?
Yeah, so I think making a transition system would be good. Okay, so what is your argument for saying that they are incompatible? Then so you have to give. We found one in which this is false and this is true. 4 is true, but 2 is.
So can I try describing a transition system instead of a computation? So I need to describe one where 2 is true and 4 is false, right?
Correct. Yes.
So suppose from every single state, I have a transition to. Okay, let me think again. Sorry.
I think Paramalai, so if I remove crosses on all these things and except I keep this only on this one, in that,
yeah, in that 4 will be true and
4 will be true, 2 will not be true, correct?
Can I describe?
But the other way around is.
The other way around is what? So we already found one example that I guess Amin or Paramal, I don't know who was that. So I think it's Amin. who, if you remove all the crosses except in the one that I have marked here, that is a case where EG of AFP will be true. No.
So can I describe a
Yeah.
So we've found an example where 2 is false, but 4 is true.
4 is true, correct.
I'll
Yeah,
try to
that we
describe
can
a transition system in which 4 is false and 2
do.
is
2
true.
is true, yes.
So consider one with 3 states. Okay, it'll be a little hard to say this over. I mean, I don't. Okay, fine.
Yeah, you can't draw pictures now, so that is something that. So why don't you make picture? Yeah, and we can.
We could take something similar to the one in 2, right? Which is already drawn there. No, the
2.
Yeah.
Here.
Yeah, we could just take the branch.
So for example, this is true. So 2.
Nothing is happening.
Yeah, 2 is something. So let me see. So maybe I have it here. So do you agree that 2 satisfies AG of EF of P? Yeah, because so
if you just take the leftmost branch and like each state is giving only one one branch with cross, then it would satisfy AGEF, but it would not satisfy EGAF, right?
Yeah, because EGF
not happening in
yeah, because here there is no requirement for you to keep repeating that. Okay, correct? Because I mean, look, each of these states is covered by this. Okay, but you can still keep nothing on this, and more importantly, it doesn't have to keep happening. If there are states following these cross states, I mean, if it becomes P becomes false after this, it is okay. Okay, in EF of P, correct? Yeah, but that's, I think, it is still not that easy.
After that one work,
yeah, after that you still have to have.
Should have.
Yeah, you should have, but it can be a different thing. Okay, see, you can have it on a different path. Yeah? Okay, so but it is not necessary. Whereas EG of AF of P requires that it has to be on the same path. Okay, so whereas here you can have these crosses covered on different things. Okay, so that is the thing. I know this is still a bit hand waving, and like what Ratnakar said, maybe having some transition systems would be good. So here's what I suggest. Okay, so maybe I'll make this as an assignment. Why don't you try getting some formal argument by saying that, okay, that these are strict implications, and in the case where 2 and 4 we said they are incomparable, you need to have some example. Means by example I mean a transition system in which 2 is true and 4 is false, and vice versa. Okay, that is one. Okay, and there is also lots of other combinations here that are missing. You probably noticed, correct? So there are combinations like AG, AG, EG, EG, EF, EF, and so on. So they are superfluous, but combinations where you have AF, AG, where G and F are flipped, they are missing. Okay, some of that we will see in here. Okay, so without proof, I'm giving one result here. Okay, where is that? So here, this is actually due to Clark and a few other people. So by the way, for this particular subject, where comparing expressive powers of CTL, LTL, and LTL and CTL. Now, Catone's book. Okay, I'm actually using this is chapter. There is expressive analysis of CTL versus LTL. So this is something that I would like you to go through. Okay, so it is quite intuitive, and so the other textbook does not spend section 6.3, and this theorem is actually stated without proof in here. Okay, so anyway, as an exercise, I agree that this way of showing it in terms of the behavior, computation tree is not a very thing. And if indeed you need to demonstrate a TS, and that I will ask you to take as an exercise. But here is, I want to address, this thing, okay, in order to show that there exist CTL formulas that are not expressible in LTL. So far, I'm just showing, by showing certain witness models that make this two formulas true in one and different in the other. That is enough to show that those two things are not equivalent. But showing that a particular formula is never expressible in that logic is much harder, because you will have to say, oh, for that particular formula phi1, say in CTL, there does not exist any LTL formula, okay, which means you'll have to do some demonstrate or some induction, okay, there exists no formula in the other logic is a much harder proof. You will have to somehow do some induction on the size of the formulas and so on. But certainly for checking for any CTL formula, if there exists a corresponding LTL formula or not, this theorem is useful. Okay, so what this says is that if you have a CTL formula phi, and I suppose phi prime is an LTL formula that you get by dropping all the quantifiers from the CTL formula phi, then either they are equivalent. If it's not equivalent either, so if they're not equivalent, then you can be sure that that particular CTL formula phi is not representable. Okay, the result says for either phi and phi prime are equivalent, or phi is not expressible as an LTL formula. Okay, so the moment you show, so in this case, AGEF of P, EGEF of P, EGF of P, they are not, so you could say drop them and then see if they are equivalent to G of F. See, G of F, what does G of F of P intuitively means? What is the constraint? G of F of P? Amin? As a linear formula. We discussed it in last.
Sorry, could you repeat?
What does GFP, the linear LTL formula GFP, intuitively?
Like P occurs infinitely.
Infinitely often, okay? So these things are, see, AG, none except AGF of P is equivalent to GF of P, okay? Because in all these things, it is, it is not necessary, okay, that you should have this kind of a cascading looping back thing, okay? And therefore, they are not equivalent. I mean, that is one way. Intuitively, I'm explaining. If you're able to produce, that is one thing that you will have to produce, okay? That you will have to produce some transition systems, or you will have to say that transition system that distinguishes, okay, this from the other one. And therefore, if you're able to show that each of these is different from AG of A, which itself is different from GFP. Now, see, now I'm switching from comparing CTL formulas to comparing CTL to LTL, okay? So there, this particular theorem is useful. So whenever you compare, so once again, you have to fall back on especially when you compare CTL formulas, the equivalence between CTL formulas and LTL formulas, you will have to rely on the proof for showing either you show two transition system that distinguishes them, or you have a proof that they're equivalent on all models. Okay, that is how you'll have to do. But to see if a particular CTL formula is expressible, there is an equivalent LTL formula, you can use this theorem by checking if, by dropping all the quantifiers, if you're able to show that they're not equivalent, then when you drop all the quantifiers, obviously you get an LTL formula. If you're able to show that they are not equivalent, then you can be sure that there is no equivalent LTL formula for the CTL formula. Okay, that is one way that you can show. So specifically, none of these things, AGEF, they are expressible in LTL. Okay, AG of AF of P is actually equivalent to GF of P. Okay, because you can actually do that. Now, that's not a formal proof. I mean, it's kind of formal proof because every state, these are the linear traces. You can look at the linear traces that you get from that, and then they're all linear traces in which you end up, P happening infinitely often on all the traces, and therefore, AG of AF of P is equal to G, F of P. But the moment you show that each of these things is distinct from AG of A of P, you automatically get the result that all these CTL formulas are not representable as in LTL, because they are not equivalent to AG of A of P, which is equivalent to GF of P. Okay, therefore you already have lots of examples of CTL formulas that are not representable as equivalent LTL formulas. Okay. So what is this slide about? Okay, let me switch to full screen. Yeah. Now, let me use this example. It's actually an example. It's a classical example that's there in the section C.3, chapter 6.3 in that Cato and Lewis. I expect you to have gone through 6.3. At the end of this lecture, today's and next lecture, I will put out expectation from you as to, after all this discussion, what the level of understanding and expertise that I expect from you. Okay. So, before getting to that, so here is trying to get an example of trying to get a proof that f of that, the other one, see, f of G of A, intuitively, what is that? Paramalai, f of g of a. G of a is, it happens infinitely often. What is f of g of a?
Eventually, G of A must be true.
What does that mean? On all paths,
Yeah, eventually a state should satisfy G of A, which means a path originating from that state.
Eventually you should get to a point on that path such that the rest of the path from there, G of A continuously holds. Okay.
Yeah.
So is f of G of A, Paranimalai, hold good for this transition system? One that I've shown here on the right side. What are the traces? I mean, one
the
what are
transition
the infinite traces here? I mean,
keep on looping at S0. In that case, that trace will satisfy FG of A.
Correct.
Because every state itself will satisfy A.
Yeah.
And if it goes from S0 to S1.
What is the other infinite trace that is possible here?
Yeah, here also eventually that.
The other infinite trace has S0, S1 followed by S2 omega, correct?
Yeah.
So there it satisfies. Yeah. So
every possible trace satisfies this property.
Satisfies f of g of a. Okay. So Ratnakar, does this satisfy AF of AG of A?
Yes. Right? Like you can go from S0 to S1 and start looping infinitely often on S2. Okay, sorry, it's AF. I think so, right?
Yeah, this is this needs a little bit of thinking. Okay, so it actually does not. So this is one example that can be used to show that these two formulas are not equivalent. Specifically, so what this says is that every path originating from S0 the states on that path must be such that AG of A should hold good. Okay. See, there is one path originating from S0. Do you agree with that? Okay, so that's what this thing says. Okay, every path originating from the initial state S0 should have states that satisfy AG of A. Should be such that you should get you should get eventually to a state from which every path originating from that state A continuously holds good. Okay, but consider this path is not omega. It's not infinitely often. Does AG of A hold good there? See, it requires that AG, every state on that path, you should have AG of A to be true. But that, every state on that, okay? Now, but S0 is a state for which AG of A is not true. Why? Because it has a path S0, S1 that goes through S1, on which S1 does not, on which A does not hold good. See, empty here means not of A, okay? See, the state S0 does not satisfy AG of A. Do you agree?
Yes.
Yeah, why? Because it has two paths originating from that. One, A holds good forever. That is this path. But it also has a path on which A is not continuously true because the very next state is not true. Therefore, on that path, S0 omega, every state which is S0 does not satisfy AG of A. Therefore, there's no way that it can eventually satisfy AG of A because it only has S0, for which AG of A is not true. Okay. You guys agree? If not, you have to ask me why. See, you have to consider the path S0 omega. First, I made the argument that S0 does not satisfy AG of A. Do you agree? If not, you yes or no?
Yeah, I agree.
You all agree? Ratnakar?
Yes.
Yes, sir.
Okay, so then S0 of, so AF of, so S0, on that state, AF will also not hold good because it requires that on every path, eventually you should get to a state, okay? And that's why, and since there is a path like S0 omega on which it does not, hold good. So it is, some branching information about, and then, that state is lost, okay? When you in LTL, and that branching information is there, which is kept in. That's why these two are not equivalent, okay? So this is good enough to show that FA AGA is not expressible in LTL. In addition to using that Clark's theorem that I just now said, but that this doesn't mean that FGA is not representable in CTL. Okay. I mean, you can use that Clark's theorem to go one way, but to show that FG an LTL formula is not representable is harder. Okay, and what I will do is, and this proof is there in that thing, and I'm reproducing it. So I'll give just the top level thing, and then we will continue next time. Okay. See, between two CTL formulas, a CTL star formula, because they both are state formulas, it is kind of easier to construct and argue the thing. Whereas here, the actual proof goes as follows. And I think, this is interesting. And I thought that's why, this would be, I'm spending some time for the first time because I have a smaller class and I've not done this in my past thing, but I wanted. So the proof actually goes this as follows. So for every CTL formula, it's actually the proof is induction on the size of the formula, because we will have to show that does not exist any CTL formula that is equivalent to FG of A. So for every CTL formula of size n greater than or equal to 0, you will have to show the following, that there exists through construction two transition systems, TSN and TSN prime, such that on one FG of A is not true, in the other one it is true. On one it is true, and the other one it is not true. But for every CTL formula of size n less than or equal to 0, those two models, transition systems, are indistinguishable on n. I mean, remove this equisatisfiability, that they are equivalent, okay, in the sense that I have defined, okay, that they are indistinguishable on phi. So then, since we are doing this by construction for every formula of size n, you have shown, and and on each of those transition systems, FG of A is true on one but false on the other. Okay, and that's how that you end up doing it. In the base case, this is this is the thing. So this works for A. Correct. So A is there's these two are for n is equal to 0. This is the two transition systems that I have now. The one on the left side is the same as one on the right side. Okay, except that the left side has a back transition from T0 to S0, and that is missing here. So FG of A is true on the one on the right side, but not true on the left side. Agree?
Yes, sir.
Because what path violates FG of A on the left transition system?
From S0 to T0 and back to S0.
Yeah, this path. Correct? Yeah. And the transition system that is constructed is as follows. Okay, so nth layer so this one is in the base case, it is for formulas of size 0. I mean, which means that it does not have any CTL. CTL formulas are always constructed using CTL operators. Okay, using either AX, EF, AF, EG, AF, or something on top of something which also already a CTL formula. So here S0, A is true of this, and not of A is true, but A is not true. Okay, that is size formula 1 of size 1. Okay, now then you construct your transition systems at other levels by putting so like this. So you have the second at the n-1th level, you have this transition system TS prime, but to that you just add this one that has this backward thing. The other one will just add just the single transition. Now next time we will see. So this, by construction, for every n, these two transition systems. Here is an example for n is equal to 1. This is for n is equal to 0. This is n is equal to 1. So in n is equal to 1, I'm taking the TS prime, the primed transition system, as the 0th level thing. To that, I'm adding one transition or two transitions, like the one that I have on the left side to this. That's how I construct the other transition system. Because I'm adding this in one and only one transition, the other, for every n, these two are still not, FG of A is true in one, but false in the other. But what remains to be proven is that every formula of size that these two transition systems, TSN and TSN prime, TS prime N, TSN is this, and TS prime N is this, okay? TS of N has this backward transition, this one does not. And, the claim is that, and that has to be proven, and that's what we'll get to. Think about that, because that proof of that is not even there in the book chapter, okay? Go through the book chapter, okay, and then, review this, the notes that I have and so on. But what I want you to, what I want to discuss with you is the proof that for every N, TSN and TS prime N cannot distinguish formulas, they are indistinguishable on formulas of size, on CTL formulas of size N plus, of size N, okay? So by size, I mean the number of CTL operators that you have on top of A, okay? So you can start by saying, so these two, see for N is equal to 1, you can start by, ascertaining or proving that, for one operator on top of A, one CTL operator, like AX of A, is the same, okay? These two does not distinguish the truth value of AX of A. And so for AFA, AGA, EF, EG, and so on, okay? And this one, and then for level 2, all formulas of size, CTL formulas of size 2, will not be distinguished, okay? And that which means that they are equivalent on these things, okay? And that's how that you do. So which means that for for any size of CTL formula, this is a generic way of constructing two transition systems on which the both formulas of that size CTL formulas are equivalent, but FG remains different on those two things. So what I want you to kind of think about, and we will discuss that together for the next class, is that why for any N, these two transition systems, TS of N and TS prime of N, are indistinguishable for all CTL formulas of size of size N less than or equal to 0. That's what I want you to think, and see if you can come up with an argument. We will discuss it next time. Yeah. Did you understand my question as to what the problem, the question that I want you to think about? If you have any question, you can ask me. Or do you understand? Hello?
Yes, sir.
Yeah.
Okay. Do you understand, that these two, for any N, they, FG of A is true on one and the other. Do you agree?
Yes.
Yeah, because this one has this local loop, okay? This on which FG of A is not true, whereas this one does not, okay? But the real thing is, why is it the way it is constructed? Why these two are indistinguishable on of size N is the one that I want you to think about. Yeah. Okay. I'll see you next time. Yeah. Thank you.
Sir,
Yes.
I think I have a transition system in which the formula 4 is satisfied, but 2 is not.
Okay.
So the other way around.
Two. Yeah.
Yeah. Can I, if I describe it, will it work?
You
It's
can.
actually a very small one, only 3 states.
Okay, so let me then,
Or I could show it.
I will use this. Okay, so let's take this S naught.
You can attach it in the chat, I guess.
Yeah, that you could do, but since we're sharing it, or do you either you have to attach, draw something like this, or you describe and I will draw. Okay.
Yeah. So state one, okay, S naught has a transition to S2 and S3. I did not describe the letters. I just said that there is a transition. I mean,
Okay.
it has a transition to both S2 and S1.
Okay.
Same thing with S1. S1 has a transition to both S0 and S2.
There's an S4.
No, only 3 states.
Okay. And then what are the transitions you have?
So S0, okay, I'll say based on what's here.
Okay,
S0,
so no, I'll make it S1. Okay,
okay,
S1,
yeah.
S2, S3. Yeah.
Yeah. S1 and S2. S2 also has a transition to S1.
Or back trans.
So make it by implies, like by implies.
Okay. So like this. Yes. Okay.
Yeah, and S2 has a transition to S3.
Okay, like this. Correct?
Yes, and S3 has a self loop.
Okay. So S3 has a self loop. Okay. Yeah.
And the start state, we can take either S1 or S2.
Okay.
So I think that satisfies. Like A, G, E, F, it satisfies because
No. What are the labels?
there. I don't think I didn't add any labels. I don't.
No. But without adding labels, how can you? What does it mean? I mean, you want at least you have to tell me what states for which A is true and what states for which A is false.
Yeah. Sorry about it. State 3 satisfies phi. The other two don't.
So let's keep it as P. Huh?
Yeah.
So here it's not P.
Yeah. S1 and S2 don't satisfy. If I by label, I meant that the transitions aren't labeled.
No. Our convention is we only label states. Okay.
Yeah. So I think this satisfies AGEF, but it doesn't satisfy AGEF. It satisfies AGEF of P, but it doesn't satisfy EGAF of P. So to show AGEF, since we start at 1, we start at S1. From S1, any path, if we reach 2, if we reach 1, we can always go to S3 and start looping. If we reach 2, we can go to S3 and start looping. And if we reach 3, we'll already continue our loop. So so P is always satisfied.
Another way, yeah. Hey, to make it, yeah. Whenever you describe CTL formulas, so let's see. So AG, you're describing AG of EF of P, correct?
Yeah.
Now, so let's look at the states in which EF of P is true. What are the states?
All of them.
EF of because EF is
because
there
all of them
exists.
can go to S3 and start looping.
Correct. I mean, but yeah, all of them can go to S3, and then there's a self loop there. Yes. Okay. So that's good. Okay.
So AGEF is the
AG of EF of P
is true for all states.
That's because, yes, that's right, because every AG, I mean, every, that's because EF itself is true. No. But AG means it has to be true for everything. Yeah, because EF is true. I mean, yes, this is correct.
So
This
I
is
have
also
a question. Now,
S2, S3. Okay, that is true. Okay, good. So Y is, let's look at what we had was what? EG of AF, no?
Yeah. And AF is only true for S3.
Correct. Because both S1 and S2 have these mutual loop, on which P is never eventually true. And this is true only for S3. Correct.
And AG of EF will be true because we can reach S3 from any of them. Like there is a path which reaches S3 starting at any state.
No, we've already ascertained that AG of EF is true for everything. Therefore, it is also true. Okay. So what we need to do is we have to compute what is EG of EF is. What is this? What is EG of EF of P?
It's
Hello?
not true. It's only true for S3. Sorry, it's actually not true for any state.
Yeah. It is.
No, it's only true.
No. It is true for S3.
But it's not true for S1 or S2.
Correct. So this is true for S3 only. Okay. That's correct. And since this is a transition, so there's no intersection. There is an intersection, but that is not an initial state.
Could you explain why it's only true for S3?
So,
EG of AF.
So if we take S1, then
No, that's not true. I think it's correct because, yeah, take for S1. S1, does it
there is a path
there
to
is a path.
S3, right? And S3
No.
infinity.
Yeah, that is true. But on that path,
every single state on that path has to satisfy.
No. Every single state on that path only has to satisfy
AF.
Oh, that which is not true.
Which is only true in 3. So
which is only true in 3.
if we're starting from a state outside S3, that means regardless of what the other states in our path are, at least the start state doesn't satisfy. And since G requires every single state on the path to satisfy, since our start state only doesn't satisfy, it won't be true, right?
I'm still confused. The path S1, S3, and S3 loops infinitely. Wouldn't it satisfy?
Yeah, S1, S3 omega loops infinitely often. So, but but AF is not true on every single state. It's not because S1 is the first state in that path, and AF
and that has a path. Go ahead. Yes.
So AF of P is not true for S1, but we require it to be true for every.
I think that is what we have to explain. I mean,
yes.
Because it is not true of S1 is because there is a path from S1, S2, and back on which P never eventually holds good. No? If it's not true of that state. It's not true of S1, neither is it true of S2. But more importantly, it is not true of S1, and therefore it is not true for this transition system. Correct, Ratnakar? That's your argument, yeah? Ratnakar?
Yes.
Yeah, okay, I think this works, yes. Yeah, so I think what I want you to do is to, do this for all things except the superfluous ones, okay? There are 16 possible combinations, right? 16? No. Yes, 4 times. Yeah, A. No, there is 2 times FG, and if you have E, and F. No. There's 4. 4 times 2, 8 combinations are there. So some of them are superfluous. I want you to do for every combination, okay? And then come up with these transition systems. The way I described it was a little bit fuzzy, yeah? We have kind of shown, but I still want you to come up with transition systems, yeah? Like Ratnakar did.
I felt it was harder to reason about computation trees than transition systems.
Yeah, it is true. See, but then if you want to make a distinction, you can come up with, but how do you show equivalence of 2 CTL formulas, say? How do you prove that for all models that you have thing? See, this business of showing witness to distinguish the 2 things is good for showing the non-equivalence, okay? That there is at least one model. But if you want to show, I think the showing equivalence, you will have to do something, yeah, for any transition system, it's a good thing. I mean, how do you show that it is true on all models? So that's something to think about. Okay, so I'm not even in the book, one to show that they are. Yeah. I mean, next class we will discuss certain laws, okay, or on CTL formulas and LTL formulas. And then also we will discuss some normal forms called negation normal form. And it is important to understand, that is one way to do. Maybe, okay, so I mean, this is something that I have not paid a lot of attention. Maybe that is the way to do, or it has to be something on generic trees or something like that. Okay, I don't know. I mean, yes, that is something that we need to think about. Okay, so if you want to show equivalence, then showing witness will not help, no?
Yeah.
Yeah, so that's where you will either have to rely on some notions of equivalence of these formulas in these normal forms. That is certainly one way to do. But whether, all formulas you can, I guess you can, because, yeah, I think that may be the thing, one way. So let's revisit this thing, as to showing equivalence. We put them in these normal forms. If they are then checked, and that would be one way to do. Yeah, okay. Good, I hope you got some idea, okay, about 2 things that we discussed, okay. One showing that they are equivalence, and then that they are not, I mean that they are not equivalent. And then there is this expressibility. And then using Clark's theorem is one way to show how to convert CTL formulas to equivalent LTL formulas, and then the other one to show that, okay, that does not exist some LTL formula expressible in CTL. I think this thing becomes, the reason for studying CTL, you can just live with CTL star, okay, because you know that it can do both, so why bother, okay? So, and then you can use that. I think LTL, if you can do both those model checking algorithms, CTL is a lot more efficient than LTL. Okay, both of them are space complete when it comes to the size of the number of states and so on. But if you fix the some kind of the size of the formula, CTL model checking is most linear in the size of the formula if you ignore the transition system. But the transition system, size of the transition systems also plays a role, okay? I mean, it's polynomial, not linear, polynomial. in the size of the formula. But the LTL model checking can get exponentially in the size of the formula itself. So nonetheless, that is the reason for seeing if there are, when you start with some property that you want to verify, it's best that you see if you can express it either in CTL or LTL rather than doing CTL star, which is hard because CTL and LTL model checking is more efficient. We will see some other classes of formulas as well. Safety properties and liveness properties that I will define. And safety properties are model checking safety properties are a lot more efficient. Okay, and that's why studying these classes of properties and classes of sublogics to express these properties is very important for you to understand. So as an engineer, if you want to, your problem will be, how do I model? That is one. We have talked about some modeling techniques. Then comes the question, oh, this is the property I want to specify. How can I do it? Either in CTL star or can I do it in CTL or LTL? That's an engineering activity, okay? Doing equivalence, checking, to see what are the paths that satisfies, that is understanding. And then, of course, you need to know, understanding the semantics and so on. And these expressiveness is purely theoretical, of theoretical interest. But for an engineer, what's important is if I'm given certain properties or certain class properties, how do I specify them? Okay, that's why we have seen some of them infinitely often. Persistence and so on. So we will look at some patterns of properties, okay, that occur very commonly in practice, and then seeing how each of those classes can be specified in CTL and LTL. And if you can do that, you always should strive towards getting it in CTL and LTL. Yeah. Okay. So that's the reason that I'm spending so much time in making you understand this. Yeah. Okay. So yeah. So that's good discussion that we had. I hope you got your things interest perked up. Okay. So see you tomorrow at 11:30. Correct?
Yes.
Okay. Thank you.
Thank you, sir.